morning, everybody. We had nice talks before talking about practical aspects of combustion stability and also some signal processing, so let's continue on these lines. So we started studying combustion dynamics that ended up as being a journey through nonlinear dynamics. We didn't plan on that, but it turned out that way. So these are my students with whom I traveled this journey, and you must have seen all of them. Some of them picked you up, some of them raised your recommendations. So I just want to take this chance to say thanks to all of them. So we'll get straight to the matter. I want to, combustion instability involves sound. It's acoustic, so there's no point not having audio. So let's listen to this sound. First of all, we'll listen to combustion noise kind of situation. So you have a gas turbine combustor or type combustor, and it's coming along fine. Now we get to the next situation. So we have got self-excited oscillations, and this is something we don't like. And this is neither this nor that. You have, it's trying to burst out, but it's not really getting there. So we saw three different types of signals, and now let's look at them carefully. So over here we have the so-called combustion noise. It has a Gaussian pressure distribution, and it is having lots of frequencies in it, so it's really not a sharp tone. So this is the signal corresponding to that, and the industry people love it because your combustor doesn't break apart, but then it causes long-term wear and tear, so that the combustor gets spoiled after 3 or 4 years after the warranty. So the company can make a lot of money in post-warranty business. So they love it. I don't think if any of you discover anything to stop this, I think company will be quite unhappy. To be very honest. Now we have combustion instability. So this is kind of signal, and the zoomed in version is right here. This is really like a sine wave kind of thing. But we have something else. I just played the audio a while back. I'll play it again. So there is a burst. We saw this kind of signals earlier this morning, and also yesterday when Nicholas was showing it. So I don't know whether you can call it the instability, but then every now and then it comes to a quiet region. It's almost completely silent here, and then it bursts out, and so on. So I don't know this because I look at the books, and the books don't speak about this. You have either instability or stability. So what exactly is this? So I am tempted to say that if I don't know anything, I'll call it nonlinear. The other day, a student failed in my class, and he came with his mother and then accused me of being nonlinear in my teaching and nonlinear in my grading. So it seems like nonlinearity is quite popular with parents also. So when you don't know something, we have to do a pilgrimage, start a journey, and this is the journey to nonlinear dynamics. I guess most of you know who this is. Yeah. So this is his grave. Actually, you can see this picture of this attractor. So what Lawrence was doing was he actually was trying to make a bare bones model for the atmospheric fluid mechanics or weather or something like that. And then he was having 3 different equations, and he was trying to integrate this. And in those days, it was done in analog computers. You have all these electrical things, operational amplifiers, and then you look at the oscilloscope and so on. And this was the signal he got. And then Mr. Lawrence went to drink coffee, and then he came back and he had forgotten to, he didn't save it, so he tried to run it again, and then he went to drink coffee. And then you see, I'm putting the 2 signals right on top of each other. So the blue one is at x at 0.1, and the next one has an initial condition which is changing after several decimals. So the 2 solutions went together till here, and then the green and blue got separated here. Now what Lawrence did, which is very interesting, is he had three variables in a three-dimensional differential equation, three ODEs coupled to each other. So he plotted the variables against each other. And then came the nice butterfly. So there was this nice topology or surface which was very exciting. So this is how the journey started. Now, are there such things in thermoacoustics? Or is this all something you read in science fiction book, or maybe science done by physicists and not so we try to look whether these things are there. So for example, in a Bunsen-Burner kind of situation, you put a duct around it and you can get thermoacoustic instability. There are demonstrations in YouTube on these things and you can do it at home. This was a PhD work with Deepika. And what we saw very interesting, we saw various different kinds of signals. So this is the simplest system we can have, Bunsen-Burner, and take glass tube and put it around. And we saw the phase portraits like Lawrence have drawn, we have drawn it. And of course, we had the limit cycle, which is what the thermoacoustic community knows about, or is very popular with. But we also have this torus, which is like the donut, or in southern India, there is a very nice dish called Viduvada. So this is that. And it's very nice, that's my favorite dish. And then there's chaotic oscillations. And so this is the classical period too. I mean, it's so beautiful that I'm tempted to believe that Lily actually took a pencil and drew this. It's so nice, unbelievably nice. So we have all these nice things. Of course, then how to analyze it. So usually, dynamical system people, they actually write equations. And they write equations and integrate them, they call it flow and so on. Or alternatively, they have maps. So in CFD simulation, I see that there are some CFD experts here. They have all the variables available with them, so they can plot anything against anything and so on. But unfortunately, the Brandlager, who does the experiment, we have one pressure transducers, and that too the sponsor is unwilling to drill through his nice combustor. At the best, he may allow you to drill one or two, and that's all we have. So how do you actually go from there to here? So that is the question. And so can we reconstruct the dynamics from a simple measurement? So a few years back, I ran into Pankaj Bhatti, who is sitting there. He's an expert in time series analysis and anything nonlinear in general. So any question you can ask him. So he explained to me how to do this. So using this concept called phase space reconstruction. So you have only one transducer, but you can build the whole dynamics from that. So what it involves is you take the signal and you actually have delays like this. So you have P of t, which is your signal. But then you have P prime of t plus tau, or you have t plus 2 tau. So you take the signal and delay it by some values, and then you can plot P of t versus P of t plus tau and P of t plus 2 tau. Now the question is, how many dimensions should we have, and what should be this tau? So the dimensions you have is called embedding dimensions. So we don't want to have 100,000 dimensions, although that sounds very fancy, and CFD people may have it, but we experiment, we like to have the bare minimum things because we can then understand things, and we also want to know the tau. So these are so there is a theorem in nonlinear dynamics called Takey's theorem. I would not go into it, but what you do is calculate the average future information. The formula looks like this, and it comes from Shannon's theory of information. So we look, it is similar to autocorrelation. Okay. I would just stop with that. So you look at the minimum value of that, first minimum, and use that as a time delay and folks well. So basically you want to try to have P of t and P of t plus tau to be as different as you want. So for example, you saw yesterday in the Wolfgang explanation about phasors. So you are having a signal which is sinusoidal. So when you draw it on a phase plane, it will become a circle. So you have sine theta and cos theta there, orthogonal to each other. So together they have the maximum information. So this is like a more fancy analogy to that. Now the next thing is the optimal dimension is one where the false nearest neighbors vanish. For example, you can look at this red curve and the blue curve. So in here, A and B looks like, so the blue curve is on a 3-dimensional plane, and the red curve is a projection on a 2-dimensional plane. So I project the 3-dimensional curve into a 2-dimensional plane. So if we look at this, A and B are lying close to each other. But if we're really looking at the 3-dimension, A and B are far away. Whereas C and D, on the other hand, they are close in 2 dimensions, they are also close in 3 dimensions. So they are really true neighbors, whereas A and B are really pretending to be true neighbors. So how do you do this? I think 2 days back, Derek had very nice explanations of this. So we construct measures. So we try to look at the distance between these points. So we try to construct a Euclidean norm, which is nothing but like a distance in the multidimensional plane. And then we see if it is converging or if it's not. So if you make this measure, which is defined as E at D plus 1 divided by E at D. So you are at D dimension, then you go D plus 1 dimension, and is it changing? And so if you look at that ratio, you would see that of course things are changing, but after some time, after you reach, for example, here 3 dimensions, you don't change anymore. Because the Lorentz attractor originally has 3 dimensions and then we are getting it. But there's a little catch. You can have noisy time series, and this may also give similar things. For example, this time series, the T1 is climbing and becoming flat only after dimension 10. This also like showed in the project meeting very nicely. So, so what we do is we try to get a measure of how much extra space this is occupying, this phase potential is occupying when you expand the dimension. So if you have noise will try to fill this thing like gas molecules. So we look for this extra incremental length which you get by adding a dimension. And we look for the ratio between D plus 1 dimension and D dimension. So we are not looking for the total length, we are looking for the extra dimension. And then that gives a good idea, because if you have a so E2 will be not equal to 1 for all dimensions if the data is deterministic. I lost the picture somehow, but I'll show you another picture later on. So if you have noise, it will always stay 1, whereas if it is a deterministic system, it will keep climbing and then become flat. Unfortunately, it's a picture what they did. Sorry. But I will have another picture with the real data will come to that. So the original attractor was here. Now we don't have the exact same variables. We don't have x, y, z. We have instead x plus x of t plus tau, and x of t plus 2 tau. And then we can construct, and every point in this attractor has something equivalent right here. So this would be called homomorphic. So you can construct the topology with this kind of plane. So now once you know that your system is deterministic, there's something called 0-1 test for chaos, where you try to create translation variables from time series as if your time series is C of t, then you multiply it by cos tc, where c is a random number, and r by multiplying tt by sine ct, and then we compute the mean square displacement. So as you are traveling and you keep computing the mean square displacement. So if you are having a sinusoidal wave like order, your thing will be bounded. So you see the y-axis limit is -1 to 0.5. Whereas if you have chaotic thing, it will keep like random walk and keep going and going. So you see the axis is spread out. Here it's -50 and there it's 150. So you keep wandering away and away. And so if you look at this distance as a function of time step, if you have a chaotic signal, it will keep climbing because it's like a random walk. It's kind of like a random walk. It just keeps wandering. Whereas if it's a sinusoidal wave, it says bounded. So then you can take a correlation between this value and the time step, and then that will give idea of whether you are, if you want it, you are near chaos. If it's 0, you are very bounded. So we are ordered system. So now, of course, we want to make sure that we don't want to. They also showed there can be a lot of fluctuations. So we try to compute for lots of values of c, just to and then take the median to make sure that we get neat results. So k equal to 1 will be chaos, k equal to 0 will be periodic. So all this is fine, but we have to see whether all this makes any sense in the case of combustion noise. So let's look at a combustion noise signal. It looks like this, quite noisy, I would say, and it can be modeled as stochastic noise also. That's another way. So you can wear a red glass and see the world as red. You can wear a blue glass and you can see the world as blue. And both will have its own benefits. For example, if you heard Nicholas' talk yesterday, he showed in quite a bit of detail what all extra information that you can get out of doing the stochastic dynamics, and he was actually able to use the noise to augment it and actually find the linear growth rates out of a system which had a noisy limit cycle. So here is the complete complement of that. We treat the whole system as deterministic and we are trying to see what we can get. So I'm going to spend half a minute on what the experiment is. So we have combustors which have turbulent flow. So we are trying to do experiments in many different kinds of systems, whether it's thermoacoustics or aeroacoustics, because we are looking at the universality of the finding. So we have a source stabilized burner here, and I want to acknowledge Wolfgang for giving me the drawings of this corner. And since we don't have too much space in the lab, I didn't want to construct another burner with a block body stabilization. So all we have is we take out the solar and put a block body, and the same combustor becomes a block body stabilized combustor. But we do have other turbulent combustors also. But these, today I show data from these two systems. And this is how the photograph of the system would look like. And you're welcome to come with me. And yesterday I gave a tour of the lab, so we can do that again today. Now the question is, are we having a stochastic signal or are we having a deterministic signal? So to answer that, we do just like what they did on Monday or Tuesday. We do the procedure, we find the average mutual information, find the time delay, find the false nearest neighbors so that we get the right dimensions, and then we plot this E1. E1 is here, so but we know that if E1 saturates, that doesn't mean it is noise, because stochastic also can lead to saturation. But then we look at E2, which is to see if the noise is actually filling more and more dimension. So E2 is also saturating, so this dimension somewhere here, but both are saturating, so we really have deterministic dynamics. And now there's a choice. Can you view it as deterministic or do you want to do it as stochastic? So for example, weather. Weather can be thought of as stochastic system. And you know that on the average, Chennai is hot and always be hot, but okay, there will be some temperature fluctuations and so on. So, and then you have monsoons and you have some kind of statistics. But if you choose to view it as deterministic, then you have short-term predictability. For example, even just by looking out, I go look out and I don't see any clouds, so I say, okay, it will not rain now for the next few minutes. And or you have weather stations which will actually compute. And I think if you're lucky, you can get good prediction to 4 days, but certainly now the technology is very good to make 6-hour predictions even in Munich, and maybe 12 hours, 24 hours very well in places where the weather is fluctuating even wildly, because the supercomputers can have enough computing power to do it. So that is the advantage of choosing a deterministic route, because then we can have predictability. Stochastic is like, okay, how many days, what is the thing on the average? So now we look at this zero on tap, and we see that the thing has, the random walk has kind of spread out, and you see the measure is increasing, and we actually are very close to 1. Actually, this is a chaotic system. Now, so in summary, I conclude that we have a chaotic series. And what is the most important property of the chaotic series, chaotic time signal? You must have heard that things are self-similar. So for example, Tanigidara asked a question where you view a map at different scale, what would you see? You would see similar kind of structures in each scale. So the nature actually displays a lot of self-similarity, whether you look at the branches of trees or coastlines, or if you look at your lungs or the capillaries, there is fractality actually. There is a self-similarity or a very large scale of very, very large number of dimensions. So it's not like your heart and lungs and your respiratory system are made of spheres and circles and all that. They are actually more what man would call rough geometry. And the nature seems to work that way. Now, of course, you can say, let nature be that way. Let the poets write romantic poems about nature, but we are engineers, so why would we care? So the question is, do we have self-similarity in turbulent flows? That is the question. Because we are dealing with turbulent combustion system, and we want to know if we have self-similarity in a turbulent flow kind of situation. So this is a picture of a volcanic eruption or something like that, and which is a nice jet in nature, very neat thing. And if you look carefully, and if you look at the kind of green structures here, and this is actually a zoomed picture of this particular one, and you see that the zoom picture shows almost identical scales as it is here. You zoom once again and you see very similar scale. So this is known property in turbulence. So turbulent flows are self-similar. If you take time series data with a hot wire anemometer or you take images, they are self-similar over a variety of scales. So the subject of fractals became very popular in the 80s, so this is a very good framework to study self-similarity. So under this topic, I think there are some people from England now. The question that is asked is how long is the cost of Britain? And there's a trick question, going back to what Tanigidara was talking about just an hour back. So if you look at the coast of Britain very far away, let's say from the moon or something, and you have a ruler and you know the magnification factor, and you try to determine the perimeter. Now you are at a high altitude, such as let's say 36,000 kilometers, and you take another picture and you have very zoomed in cameras, and then you try to find the perimeter. Now you come down, fly on an aeroplane like spy plane like SR-71, 28 kilometers, take a picture. Now you come down to transport aircraft, take a picture. You keep coming down. Now, depending on the size of the stick, the perimeter will keep diverging. So you actually see an inverse power law, that is the coast weight does not converge, it actually follows, and if you have a log plot, you will see what is called inverse power law. And this slope of this curve, this is called the fractal dimension. Okay? So this is a real thing. This is not some geometry where we wrote some code with MATLAB and made some signals and all that. This is as real as Britain can be. I mean, you take a photograph of Britain and you measure the perimeter. So now, see, we know about fractal properties of geometric objects, but now we don't have a geometric object, we have a discrete time series data. Okay, so is the time fractal? Okay, that is the question. So we do something called deep rendered fluctuation analysis, or DFA. Earlier, I think people were doing wavelet transform and so on, but this is the most recent one and is considered fast and very good. And this has been used in many medical imaging instruments, very successful DFA. And so what we do is take this our signal or time series data, and then so on the top we actually have a combustion noise signal, and this is like a monofractal time series. So we will wait till we see what is actually combustion noise, and then we have white noise. So white noise is no correlation, just white noise. That's mathematical. And then what we convert it to a random, we keep on adding the values. So then it will become like a random kind of signal. So that is this line over there. So we keep summing the values. So you get a random walk-like signal, that's what it's called, random walk-like signal. And then we divide we have a time series and we divide it into small segments. We strip into small segments. And there are some guidelines with it. So it's, you look at it over the range in which you are interested, where the cells in the ID. So, and then we detrend locally. For example, if in this case, you can see there's an oscillatory pattern, but there's also a linear fall. So we can remove it. So we detrend the local fluctuation. And then we try to find the RMS value of each segment. And there are a lot of segments, so we take the average. So you plot the log of RMS value, log of the segment size. So this x-axis is kind of like log of time. And we see that the log of the RMS and log of the time or segment size, that will diverge. That is exactly what you see in fractals, because these quantities, like RMS, they will not converge within a cutoff. There will be upper and lower cutoff within that range. Then you don't converge, they keep increasing. So this is very good, very useful quantity, because the slope of this plot of RMS versus time, that gives what is called Hertz exponent. So there's a rate of divergence slope over this time. Now, of course, if you go to very big value, and everything will converge. But we are looking deliberately at the region where it's diverging. We want to take advantage of this fractal time. So the slope of the curve gives what is called Hertz exponent. And Hertz was you are studying how dams were getting filled, and he came up with this under that context. And 2 minus x actually gives our famous fractal dimension. Now, there are different kinds of signals. For example, this is what is called a persistent signal. So the value is going up, the next value will also go up. The one after that will also be high, the one after that will also be high. And you hope that when you buy stocks, then you keep going up. Of course, the reverse is also persistent, because you are going down and you keep going down, going down. You always, when you buy stocks, you want to keep on going up. So this would be like a persistent signal. So now you have white noise, which will have no correlation between the signals. If you go up, now next thing can be come down, or it can be go. And if the next time step is up or down, doesn't matter. Down after that will also be random. It will have no correlation. As opposed to anti-persistent, where you go up, you are bound to come down. You come down, you are bound to come up. So this is like, I can imagine that sound would be like this, because sound is expansion and contraction, expansion and contraction. So very likely this would be, I can imagine a sound and a combustor would be an anti-persistent signal. It is that's what it intuitively feels. So we can classify the signals as persistent, anti-persistent, and these are absolute bounds. So below h equal to 0.5 you have anti-persistent, and above h equal to 0.5 till on it's persistent. Now, combustion noise as anti-persistent fractal attributes. We saw in this earlier curve. Let's go back. So the top one over there is combustion noise. It has h equal to 0.32. In fact, if you take the data from many different combustors, it will all come around 0.2 or 0.3. It can't go to 0.5 because that is white noise. So it's white noise, there is no correlation, but for combustors all below 0.5, and it can't be below 0 because 0 also has to limit. So, just to summarize, combustion noise actually has anti-persistent fractal attributes. Now, signals with single scaling behavior are called monofractals. You must have studied about Cantor dust and Oak Island and so on. But then nature is more complex than that. I mean, we can't simplify nature to that. So a monofractal description was, people, as soon as the fractals came, people tried to use it to study turbulent flows, and there was quite a bit of excitement. But then eventually found that a monofractal description is one fractal dimension was not adequate to describe turbulent flows. The same with physiology. People try to come up with fractal description of heartbeats. That is, in the heartbeat, you look at the variability of the heartbeat or signals in the head with the EEGs and so on. And initially, there was a lot of enthusiasm. Lots of papers were published in the 80s with monofractal analysis, but then found that there were some problems. So, and then later, in the late 80s, it was shown that turbulence was actually multifractal. Now, what does multifractal mean? Well, the small fractal and large fluctuation. So, different scalings for different amplitudes. That is like a simplistic way of explaining this. And there are very nice papers in the late 80s, particularly there's one by Srinivasan from Yale in 1988. There's a very nice JFM paper. It's almost like a review paper, 55 pages long. Very nice paper. So this is a well-established thing. Now, just want to remind you once again of what is Hurst exponent. So we are plotting log of RMS versus log of time, and you get the slope, and the slope of the log plot of Hurst exponent with time scale is what is giving Hurst exponent. Now we want to see what more can you do with the scalings. So now we need to pick up how small amplitudes should scale, how large amplitudes should scale. So we want to selectively, under some cases, prefer small amplitudes, and selectively, under some cases, pick up large amplitudes. So the simplest way is to raise this thing by a power cube, and then take it, add up the sums, and raise it by 1 over q. Now, if you raise by a higher power, it will favor the large amplitudes. But if you raise the signal, that is powered by a negative number, it will favor the small amplitude. So if you do that, then q greater than 0 would focus on high amplitudes, q less than 0 would focus on low amplitudes. That's straightforward. So this is called structure function if you want to use fancy jargon. But it's same as standard deviation, but just generalize with a power cube and a power 1 over q. Nothing more than that. Okay? You can intuitively understand this. Now, so if you look at the variation of Hurst exponent with the scaling exponent, so we are using different values of q, and we'll see if you get the same Hurst exponent or not. So we look at white noise, and for example, we do the calculation for lots of q's, but I picked up 3 values so that we can see. So here I put q equal to 0, q equal to 5, q equal to minus 5. All 3 have the same slope. Now the slope is 0.5. Now we look at a monofractal signal, and all q's will cover the same slope. That would be, that's obvious because there's only one fractal dimension. So you look at periodic has only one scale, so eventually there is no divergence or anything, you should get a slope of 0. So that is the limit. Now if you look at combustion noise, different scalings are giving different divergence rates or different slopes. So combustion noise doesn't have just one divergence rate and many divergence rates. So this is called multifractality. So we now construct a spectrum of fractal dimensions. We have a collection of fractal dimensions, each favoring different amplitudes. So now we put everything together. So in the because you have several q values, each is having a different slope. So in the 90s, what they did, early 90s, they plotted q versus hq, and you get a spectrum like this. But of course, mathematicians, they love to write theorems and look at the beauty of the things and then make it more and more beautiful. So eventually, they came up with this formula. That is, you have to plot f alpha versus alpha, where alpha is d tau over dq, where tau is qhq minus 1. Now, that's all formula. Let's forget about the formula. What does this picture mean? Now, at each, there are different divergence rate. So what is plotted here is the divergence rate. Now, what is on the y-axis is the relative contribution. So for example, and the maximum is non-measured one. So this divergence rate is the maximum divergence rate. And then at this particular divergence rate, you don't find it so much. And this much, you don't find it so much. So you have spread, and it's telling how much it's happening, how much there is one divergence rate, how much of it is in some other divergence rate. So in summary, combustion noise actually multifactorial. It has a spread. Now, I was very excited. I thought I made a major discovery that was done together with me. But I always have friends who have a knack of putting me in my place. They punch me on the face whenever I say I made a discovery. Say, so what? Great. Okay. So we are engineers, and engineers are supposed to do useful things. Okay. So then, what is the use of this? We can say it's multifactorial. They will write 10 theorems on it, but what is the use? So now let's go to combustion stability. You are having a combustor and running, and it's noisy, and that's fine. Like I said, we love combustion noise. It gives you post-warranty revenue. Now you keep on increasing, and the amplitude is going increasing. This is data from a real experiment. Now at this point, you want to know what happens next. Is it going to keep on increasing as a general increase in combustion noise amplitude with airflow rate, or is it going to jump to instability? So you don't know. So that is a trick question. Now, so are we going to go like that? In which case we are very, very happy. In fact, the combustion noise amplitude is increasing a little bit more, so we get more post-warranty revenues. Or are you going to keep on going like this and back going to instability? Now, this situation you don't want, because you will break engine parts, you will break turbine blades, you will break all kinds of things, airlines, and then the machine has to be shut down. So even if you detect this instability after it comes up, then what does the operator do? He'll trip the machine. And then you'll have to wait for half an hour for the engine to shut down, and then restart it at another half an hour. That would mean a lot of lost revenues. And then of course, the power operator actually has written the contract such a way that the gas turbine companies have to pay for the lost power. So everybody is under difficulty and the lawsuits and so on. The amount of money lost every year is of the order of $1 billion. And each company loses around lots of hundreds of billions. No one exactly tells how much exactly it is. But it would be really nice to know right here, not after the amplitudes have come up, before it's coming up, that is go and this is no go. If you do that, now yesterday Noah explained some of the strategies with which you can control NOx. Everybody knows this. But the thing is, by the time you find the controller finds that the oscillations have come up, it has already come up. You cannot get rid of it because it's come up, it's gone. So you really want to find out the correct prediction, whether it's going to go unstable or not. Now, you have identical symptoms. One case it's combustion noise going up steadily. In the other case, it's suddenly the amplitude goes up and there's just a frequency of that. We don't know which is which. Now, this is seen, same problem studied by the medical community when you have a chest pain and then you don't know if it is a heartburn or a heart attack. And there's a big question. Because many times people have called 911 and 108, whatever is the number, go to the hospital, and when you go there, you look like a fool. They give you antacid and then send you back, and then later you get bad bills for the ambulance and the agency care unit charges and so on. On the other hand, the many people who thought that this is only heartburn took an antacid, and they never woke up, and their families were left to gain. So it would be really nice to know which is which, but you don't. And if you ask many of the interns, they all have a lot of guilty feeling because in the hospital they diagnose wrongly. So what we want to do is not diagnose but prognose and the onset of an impending heart attack. Because once you have a heart attack, you go to the hospital and they tell you like you had a heart attack. You look like a fool because you know if you had a heart attack, you should have told me earlier that I'm going to get a heart attack. Now similarly, I want to get to know whether there is an impending instability coming. And it's very important, I've highlighted the word impending because what I want to know is whether I have an impending instability and not really an incipient instability. When we say incipient instability, that's what the FFT show, that the amplitude has gone up and then you know. But you know anyway because instability has come. So what is the use? So you want to know that there should be whether there's impending instability. That the instability is not born yet, but can you find out whether it's going to happen? And incipient means already born, so it's too late. And anyway, that's what everybody does. They have put controllers in the engines of the test rigs, and then you say that there's instability, and then, but it's too late. So it would be nice to have some kind of astrology or something. You can forecast what happens to you. So now the question is, you want to listen. As an engineer, tell whether a combustor is going to be unstable or not. I can just hear. I don't even have to hear. I can feel it in my body. Now, of course, the way the modern, when I was a kid, when I had illness, I would go to a doctor. Doctor will feel my pulse, stethoscope around me, and then hear my lungs and say, okay, this is the problem. But now they don't do that. As soon as you go to the hospital, they catch you and put you inside these machines, and then you get this fat bills of this scan and that scan, and doctor doesn't want to see you. He just wants to look at the damn reports. And he just wants to get kickback from the scanning company. At least that's a very common thing in India, and there's a lot of practices. So I want to listen and forecast the instability. Now I have a lot of emotional reasons for saying this, and I went through a lot of emotional trouble to make the statement. I did my PhD in laser diagnostics, and I can do PIV, LDV, play all kinds of things. But you know, it's like you scan the patient, but you can't tell them anything. So we always, I remember in the 80s, the paper said that okay, now we can do wonderful things, and a little bit more improvement in cameras. And at that time we had a line arrays, and then he said, something they said is if you have a square array camera, you would solve all the problems. Then came 128 by 128 pixel camera, and then everybody said, we have to wait till you have 256 by 256 camera, and at the moment the high-speed cameras can do 128 frames per second. We just have to wait till it's 512 frames per second, and then all problems will be solved. And it's the same thing now, 20 or 30 years still. I mean, the combustion instability is staying at large. If that was not the case, Mr. Sundar won't be coming for this meeting. The problem is very much there. And you can have more laser diagnostics. Now they have 5 lasers and 18 cameras, and you have 3D thing. And you can actually see what is the flame. If you sit inside a combustor, you can see all kinds of fancy things, but you can't still tell. Well, if everybody says they can tell, but they can't really tell. That is the thing Sundar's role. So let's go back to this sound, and let me tell you a personal story. So I was doing this experiment. No, I didn't do the experiment. Vineet was doing this experiment, and I offered to help Vineet to do the experiment. You know, as a professor, you push your graduate students faster, faster, faster. And then I said, okay, Vineet, okay, you come and help me. Then after a few runs, I was really driving him crazy. He and the other force people. If you are here, nothing is moving. Either you spoil this or spoil that, you're not able to experiment. You do one thing, you stand in that corner and you can watch. You cannot do anything more. So he's sending me to that corner and I'm watching. So I'm standing here and I'm watching. And after 3 experiments, because our experiments last for like 30 seconds, 45 seconds, and then we stop, and then we wait for it to cool and they can start again. So after 3 experiments, I understood that Vineet knows when the instability is coming. Because as it is approaching, I can look at the shoulder, because I'm right standing on the back, and he won't let me come anywhere near, so I can watch his shoulders very well, and it is just tightening him. You can see the stress. And then, when the instability comes, he is cool, he is relaxed. Okay. I mean, instability came, now I can take my data and graduate. So, after a few times, I mean, I was there for 7 hours. It was in the beginning very exciting, but they wouldn't let me move from this corner. Really, they were very strict about that. He's usually very cool, but this particular thing is very strict. That I shouldn't do any experiment because he's very worried about my safety plus his experiment. So after some time, in the beginning, the excitement of watching Vineet's shoulder, but how long can you watch Vineet's shoulder? So eventually, I just went to my room, which is not too far. You can hear the sound. Now I started to play this game. Now, I am able to tell when the instability is going to come. I know it's going to come. Sometimes you don't need, and you know it won't come. And then I got very good at this game, this ballistic, which is something which I don't even know it's distinct, because I have a feeling that your body is sensitive to pressure, and if you speak to gas turbine operators in the field, they will feel it in their body, because it's like the martial arts people, they can sense people coming from the back, or the sportsmen, they give low lip passes, because there's some kind of feel on the skin, and so I think that's even more sensitive. I actually can feel it. It's like a feeling, and you can sense your hormones. So now there was another student, not my student, he was having a combustor which was doing this. I asked him, okay, when are you doing? He said, okay, next week I'm coming. And then I was listening, and I could make the prediction, and they're even better. So now I was very clear that there are precursors, because you know, without any magic, you know when it's coming. Not only me, everybody in the lab seems to know. So now I will show you this field. I'll try to transfer this field to you by playing this sound. So this is combustion noise. It's like a roll kind of sound. So now this is instability. This is like you would turn on a loudspeaker, connect a sine wave to it. Now let's look at the signal in between, when we need shoulder or string. You can sense that it's trying to come. There's this bursting. And that's really loud because there's a low frequency modulation which you can just sense. And this is what gives the feeling. Now, can you have tools to do this? Those are the questions. But there's a precursor. There's a real way in which the instability is happening. So now let's ask some very basic questions, because you look at this eigenvalue network model and then all these things, but they're all sophisticated. Just forget all that. Just as a child, you have to ask. I asked. At least I am very stupid. I want to ask. So what is stable operation? What is unstable operation? We are looking at the transition from stable to unstable operation. So stable operation is what we call combustion noise, or what I would call combustion chaos. And then we are going to full-blown instability. The issue is how is it going? So when you ask what is combustion noise, I think there are lots of tests, not just the ones I showed, there are several other tests which say that it is actually chaos. And what is combustion instability? It is actually periodic oscillation. We know it's trivial. So then, how do you transition from chaos to order? So I have my friend Wolfgang Philipp. He was a very organized person, very neat outfit, and me on the other hand is a complete mess. So the question is, if he lets me run in his room or home, he has let me stay in his home when he was not there, you can imagine that what would have happened. But is the reverse possible? Can my room ever become like Wolfgang's room? Now in combustion instability that's possible. Combustion noise goes through intermittency to full-blown instability. And intermittency is not just some term you know, I mean engineers know. You go this way, but there's more to it than the English word that things are intermittent. It's actually a dynamical system state. We have studied it quite a lot, but I'm not going to talk about it. But there is a well-defined way in which instability goes. Now I want to do an experiment. So I brought some acoustic devices. So these are flutes. I will try to see if we can demonstrate intermittency to you. So there's no combustion yet, but let me try. So this is like chaos. I mean, it's not really a nice sound. And nice sound would be, that would be tone. But this is like, that is this noise being modulated by the pipe. Now, I'll try the in-between thing. It's very hard once you learn to play. Can you hear the worst kind of sound? I will try another one. Some people can detect some frequencies better. I'm not modulating my blowing, but it's coming. Now, this is foo, and so that is tone. Now, when I started learning the flute, initially it was all foo, and then came intermittently, and then came the tone. So I know everybody knows, but everybody, you don't need to learn to play flute. If anyone who knows is playing flute, you have to be suffering through this. And so there is something beyond combustion instability. When we speak to gas turbine engine people or rocket people or industrial furnace people, they will say that you have to do the experiment at 53 bar because that's where my experiment is running. And whatever is happening at 53 bar has nothing to do with what is happening at 23 bar. But where is a flute, there is no combustion. Now you can take a water bottles you have and blow this, drink some water, then blow this, you can demonstrate this. We can have, I think there are experts here in pipe orifice systems, internal acoustics of low Mach number flows. There also this happens. Any kind of place where you have turbulent flow causing some kind of noisy situation, to order or instability, this is happening. So this is not just in thermoacoustics, but in any aeromechanical instability. So we know a very general way in which this can happen. So if you can catch this and if you can describe this, then we have the precursors. And then there's a much more much deeper level of understanding, which is, agreeable with my intuition, because when I learned to play flute, initially I couldn't play, then there was a time where I could intermittently the notes were coming, and then it became neat sound. And that's the same with combustors, any kind of oscillatory thing. So we did experiments in aeroacoustics, aeroelasticity, flow-induced vibrations, surge, everywhere the same route is happening. So the issue is it like a discrete thing, or can you get a smooth measure? Because we want to know smoothly how it's going. Then only we can get a precursor. We want to get some kind of idea of how far away you are from instability. Because you don't want to say, okay, now it can come anytime. No, we want to know some kind of parameter which is very smoothly as you go towards instability. So we look at the Hertz exponent again, and we look at it for the solar stabilized combustor and block body combustor. So we know that it starts on some value below 0.5, but somewhere around 0.3 or 0.2. And then 0 is sine wave, so it should come very close to 0, because in reality you don't get perfect sine waves, it will be close to sine wave. So you are actually coming down continuously from some value like 0.3 and coming to coming close to 0. And this is for a block body stabilized runner which we have. It's coming more or less like a straight line. And 0 is like an absolute number. Any instability anywhere, Hertz exponent has to come to 0. And any kind of turbulent flow, making any kind of acoustic or that kind of behavior has to start from some value below 0.5, 0.3, 0.2, okay, the precise value we can debate. And now you see, the pressure amplitude is rising at some value here. Now, but well before it, where if you look at this with your FFT controllers, I cannot make out, nor can any of the controllers make out that instability is waiting here in the corner. But look at the Hertz exponent. It is plummeting while this pressure amplitude is not doing anything. Because it can pick those bursts very, very clearly. Now, so as we approach an impending instability, we see that the Hertz exponent is dropping very rapidly. And it's going to an absolute value. Any instability in the world, whether it's 53 bar or 83 bar or 10 bar in India or China or Japan or America, it will go to 0. Now, the multifractal spectrum, that means, in a turbulent flow you have lots of scales. That will actually collapse to one point. And we know intuitively that when you have multi-scale form, it is shrinking to one scale, because when there is combustion instability, there was always a sine wave. So this is going to shrink to that. So combustion instability is actually the loss of multifractality. So now we have this question again, are you here or are you here? We can actually tell that this is the problem. And now we have made controllers, we can actually go close to it and then hold our combustor there, or we can take evasive action. So we have put a controller and so on. So we have also not only in performed experiments like I just performed in an aeroacoustic system, we have actually taken data in a pipe tone, and there also, okay, I could show you the Hertz exponent when I'm going through, but here we have measured, and here, for example, the amplitudes are staying fairly steady, but the Hertz exponent is dropping, and we can actually tell very well in advance. So we have many more pending precursors, and they're based on sound theory, and this can be transferred to the industry, and then we wish to help stop instabilities, because we can, the way you avoid instabilities, you have big margins. And then we saw yesterday that the problem with big margin is you have a lot of NOx production. So here you are having a tight control of the distance, so you can put a nice threshold and you can go much closer to the boundary than normally you have to stay away because you are afraid that you don't know exactly where it is. But now you know exactly where you will become unstable, so you can come very close to that. And so we have a system, we have developed a controller where you have a combustor, you measure with one pressure transducer, just only one transducer, and we can calculate lots and lots of exponents, and we get some different things. There are some which are very early warning, and then some are late warning. And so we can use this, it's like traffic lights, you have red, yellow, and green, so like that you can put different warning systems, and then that gives the operator a much better control over what is happening. And so it has been told that combustion systems are complex, but people just pay lip service to it. But really you need to, like yesterday Noel was showing, he used the theory of stochastic different equations to describe complexity. That is one way of describing complexity. Here I am using another approach. So we really have complexity, and we shy away from this complexity by treating it as simple sine waves and linear systems and so on. But it is a very complexity that is giving us early warning, because combustion instability is nothing but loss of complexity. So I think we should not shy away from it. We should build theories based on this, and we should build devices based on this, and I think we can benefit a lot. So now I have come to the almost to the end, but I just want to say one last thing. I will ask a question: what is common between heart attack and thermoacoustic instability? Now, when instability is coming, I'm sure the scientist or the engineer, they are having a heart attack. If you have a rocket engine going unstable, people are standing kilometers away, but some have told me that they thought they will die because they couldn't know what it was. It was such a road. Apart from that, more seriously, is there anything common between heart attack and combustion instability? So, transition from combustion noise to order. Instability is actually order. We don't like order, but it's going to order. So, no wonder my room is so messy. I don't like order. So, transition from combustion noise to order corresponds to a loss of multifractality. Now, congestive heart failure also corresponds to a loss of multifractality. So, there are tools available, and there are some much more common thing than combustion instability. It has lots of commonality with lots of other things, and we are somehow so worried about what happens at 50 bar, what happens at 48 bar, but in that we look into the trees and miss the forest. That's what is happening. And the other fields are much more advanced because they're not specifically looking for so much detail. This is an advertisement from Toyota, where the problem with detecting heart attack is having machines in the hospital to detect heart attack. I wouldn't go to hospital to check if I have a heart attack, if I'm living fine. I would end up in hospital after I got a heart attack. And then it is too late to detect it because I already had an attack. It's like, what is the point? So what the Japanese are very smart. So they actually put, Japanese drive a lot, so they put electrodes on the car steering. And then they have this processor. So as soon as you're on your car, you get a mini checkup whether your heart is fine or not. And it is serious. I mean, all the high-end Toyota cars have this thing. And if there is a heart attack, you can predict up to 4 days before. So if it senses that you're going to have a heart attack, if you turn the ignition, it will not start the engine. And if you are driving, and every now and then it checks if you're on a long distance drive. And if it senses that it's going to have a heart attack, that's what that shows. It'll stop the car and call the ambulance will come. But if you're having it 4 days morning, then you can go on your own. So, I mean, if they can do it for a heart, which is much more complex system, and working well, you can buy this product. You can buy a Toyota, which will let you live. So you can implement this in combustors or places where you get surge or turbine aerovelocity, any kind of vibration. This is a universal thing. So I'm at the end of my talk. What have we done? So I'm going to summarize this. So combustion noise is deterministic here. That was my first point. And we have a multifactor spectrum for the combustion noise. Okay, well, I forgot to make one clarification. I'm not looking at open flames in the middle of nowhere. I'm looking at flames inside a combustor, which is what this community is interested in. So instability is like a loss of multifactor. You had a spectral reserve which shrunk. You had a spectrum which is broad which shrunk. And that was detected in several indices. We have a universal path to instability in turbulent systems. We have combustion noise where intermittency to full blown instability, and I showed that in my notes. But the most important thing I want to say, when you have a signal, we immediately decide that the signal is consisting of what we call the proper signal and noise. So when you get something which we think is having signal plus noise, we split it into signal and noise by several different techniques. And then what do? We throw it into the dustbin. We remove this. But don't trash the irregular fluctuations. That's really having the crux of the matter. It's what gives you early warning. And we should not throw it. It is really, really valuable. And we can do analysis and predict online and put online predictors. And this is really valuable. So that's the end of the talk. Thank you very much. We are happy to
We now have time for a few questions. Please speak into the microphone. this prognosis that you have done, that prior to the instability you have chaos, that is good for turbulent when you have turbulent combustion. But for laminar, when you are having laminar jets and combustion over there,
you have to feed it with noise.
Yeah, so
but in laminar combustion, no one is interested.
I know. Everything that is
if you seed it with noise, and then you can get precursors. This is there in the classic work of Wesenfeld and so on. They put noise into the system, and then there are a lot of some papers that we others we a long time back.
But once you put noise, it becomes stochastic. The point I am making is that prior to the instability, when you have turbulent jet, there is noise that is coming from turbulence, and that itself, okay, you can say that there is some deterministic chaos from there, and once you get into an instability, the dominant mode comes because of the instability. So there is a transition from chaos to order. But if you are looking at systems where the pre-instability thing is fairly standard, like a laminar jet, laminar flame, then probably this prognosis will not work. But for real practical combustors, most of them are turbulent combustors. Probably. All of them. So okay. So then this is.
So I am not given up on laminar. I don't give up very easily. So I am coming to Kanpur to deal with laminar. There may be something. Yes.
In your charts, you showed some Reynolds numbers. So how was that defined? Can you go back to your charts? Yeah. In all your first fact,
It is based on the mean airflow rate.
So your hypothesis is Reynolds number necessarily changes when you have instability?
No. We are purposely taking them out. So we are having airflow rate and fuel flow rate, and we increasing the airflow rate. That's a continuous result.
How the bifurcation is? So essentially, in an experiment that you've done at the lab, you have control conditions to explain.
Yeah. In a situation like in the industry, there it will be free because you cannot touch your airflow rate if you are having a land-based gas turbine engine. You are lowering the fuel flow rate, so the bifurcation parameter will be equivalent. So it can be any bifurcation parameter. It doesn't matter.
But you've had experience where he has not changed and you have.
Yeah, then you must be changing something. I can give many examples.
So that's what I would like.
Yeah. So for example, the atmospheric temperature is changing, and you have dampers, and dampers are optimized for the generally, if it's a cold country, it's optimized for cold conditions. And then the weather is on a unfortunate day, the weather heats up and comes to. Sometimes you get 35 degrees in Germany, and then the damper goes out of tune. Then you can get instability. So the bifurcation parameter is outside temperature, or you change the gas. So you have gas from Soviet Union coming, and then you are changing over to gas from Ukraine. And the change happens over 30 minutes or so. So there can be anything. So one way to see this, normally the instability happens so fast that you are not able to check what happened. So now we have a quantity H, Lodge exponent, or many other things. And you can look at the derivatives with respect to gas turbine companies are monitoring all kinds of things. So you can look for dH by d alpha, where alpha can be any parameter. And then you find which one is it that actually caused. So there is much better chance of diagnosing what happened.
The problem is in a practical situation, the parameter that you think alpha, it's not going to be this small.
It doesn't matter. I don't need that. I just need the signal. I can tell whether you are going to, if I'm having, let it be whatever parameter, I don't care. If I'm having a first exponent of 0.3, I know it's safe. If it is coming down, I know that I'm going to instability. It doesn't matter. I don't need to know the parameter. That is the beauty of the thing. I don't need to know the parameter at all because the distance to instability, it depends on the physical situation. Some cases it can be Reynolds number, some other cases it can be equilibrium, some other cases it can be atmospheric temperature, some other cases it can be fuel, some other cases it can be heat transfer. It doesn't matter because these measures are absolute measures. So it doesn't depend on this technique at all. And for example, if I same thing works in a fluid as a combustor, why would it depend on the equivalence ratio? Here there is no equivalence ratio at all. But the same index works. It's a universal description of the distance to instability. I don't need to know that. But if you want to know, to fix it, then you find the dH over d alpha. And there are lots of parameters, 15 different parameters, but you're monitoring them. And you find the partial derivative. And then you can, you have much better chance of diagnosing than if you didn't calculate it, because anyway you're not able to tell. It's by the intuition.
So, but this thing about this thing, linear they can feel it in the ears, ear feel it in the body. This is exactly that. Yes, Sachin.
You said that if you have a noisy signal, you have to throw out the noise and.
No, I'm not saying everybody throws it. I'm saying don't throw it.
Okay.
That's the dollars.
Okay.
I had a picture of dollars, but maybe it was not here. It's the value is in the noise. Or I wouldn't call it noise. It's the irregular fluctuations.
Yeah. Okay.
So maybe we can take one last question.
If you have a configuration and you change the operating conditions and you approach a region where you have the possibility of having two different modes excited and that the system is not really choosing one or another, what will the Hurst exponent will say? Because if you have two, it's there will be.
See, it depends on how you calculate the Hurst exponent. So it's over the scale. So it depends on, you can choose the scales to detect instability in various modes. So of course, if you don't know anything about the thing, see, we have to have there's some range in which you look for the scaling variance. And you set your mode correctly and look for that. It's possible to do. Well, I hope we do.
So therefore, you would apply to the same time trace two kind of analysis with different scales to get an Hurst criterion for one mode, one potential mode, and
if they are nearby, one will be enough. You will find it. If they are very far away, you will have to change it. I mean, if you are having 100 hertz and 2000 hertz, then you will have to apply a little bit different, but it can be sped up. It won't cost extra time. That's not great.
I think what he's saying is that suppose at the onset of instability, instead of a single mode going unstable, if there are multiple modes which are going to be unstable, then you will not have proper order even in the instability. When the instability is set in, it will not set in as a limit cycle, but it will set in as a more complicated.
If it comes as a period 2, we can detect.
Not period 2, but suppose it comes as chaotic. Then
it's coming this way. It's already chaotic and it's instability order.
No. The lower one, actually when you go from stable operation to unstable operation, actually the pressure suddenly jumps, okay? Some criticality is there and all.
So this can be a problem. It is coming via quasi-periodicalism, but it doesn't come.
Because there are configurations where at the instability itself you see quasi-periodic. So you can as well see chaotic also.
See, in laminar systems, not in turbulent. In laminar systems, you come to the state via intermittent. Okay, you give me a case.
We can actually in machine tool chatter it happens. So
yeah, as I said, this is true only for situations where the thing is driven by turbulent flow. Okay. That is not the case in machine tool chatter. So there are several other. This is general only for cases which is driven by turbulent flow.
No. What I was saying is that when machine tool chatter happens, when you get instability, there are some cases where the first time that you see instability itself is a chaotic solution. So
it is possible in laminar to bust what you're saying, but in turbulent, I mean, it's more difficult, but actually understanding why seems to be more easy. I think we need to go to
I'm afraid I have to do the duty of a good docking student and stop further questions. More likely can't take the wrong, but yeah, let's thank Professor Sridhar. So next we have Professor Simone. We're talking about applications of
They have given to Ashik.